let's just talk about these waves in general. So everything from this point on is regarding all types of waves, any type of wave, compression wave, transverse wave, the other types of waves we haven't talked about yet. Let's talk about the wave speed. And when I talk about the wave speed, I don't mean how fast the, let's see if I can get this to go again. I don't mean how fast the particles themselves are moving. I mean how fast the wave itself is traveling down toward the end of the slinky, or how fast these sound waves are traveling outward from here. So that wave speed can be quite variable, can be very different depending on a lot of different things, but this is a really important concept to know. The speed of a wave, whatever it is determined by the medium through which the wave moves. And some of you might be like, well, what's a medium? Well, I'm not talking about a spiritist. I'm not talking about a person that can see the future. A medium is simply the stuff that the wave must travel through. And there's lots of different mediums. The medium for my sound right now coming to the computer is air. Sound waves are traveling through air. That's the stuff the wave is moving through. Sound can also go through water. Water waves can go through water. Electromagnetic waves can go through water. That's the medium that the wave moves through. Space, which is a vacuum, is actually not stuff at all, but it still can technically be a medium because there is one kind of wave that can travel through space, and that's light. Sound cannot, water waves cannot, but light waves can travel through space. Earth, glass, your body tissues, if you have an ultrasound, lots of different things can be the medium. So the medium is the only thing that determines the speed of a wave.
Okay, so here's what I mean when I say that the wave speed is controlled by the medium, right? And I know that's a strange way to say that, but that's true of all waves. So this rope represents a wave, so what's going to happen is I'm going to simply send one wave pulse down to the end of the rope, and I just want you to kind of, in your mind, visualize how fast it gets there. Maybe you can count how long it takes to get there. All right, ready? You see how long that was? Do it one more time. About how long?
About 1 second.
About 1 second? So you can see how long it takes to get there, right, Jace?
1 to 2 seconds.
You see the wave that it travels down to the end? So here's the question. What can I do to make the wave get there faster? What can I do to make the wave go faster? Flip it
harder.
Whip it harder? That's what a lot of people say. I would have done this in class if you were in class, and I have a big rubber band rope, and most of my students say, flip it harder. So let's try that. Let's flip it harder. Remember how fast we went the first time? I know that's kind of weird for you, but did that change the amount of time it took to get there?
No,
so let's do a small wave. Big wave. Small wave. Big wave.
Yeah, it's just changing the size of the wave.
It's changing the size of the wave, but what's it doing to the speed of the wave? Nothing.
Yeah.
So flipping it harder doesn't change the speed. What do you think I can do to change the speed? So the wave is controlled by the medium. Remember that the medium is the thing that the wave is moving through. What's the wave moving through? What's the wave moving in?
The rope.
In the rope. What can I change about the rope?
That you could make the rope shorter.
You can make the rope shorter, or what if I do this?
Okay. Oh yeah, you can stretch it till it's perfect.
Yeah. So what I've done is I've changed the tension. See, when I was like this, there was very little tension. The rope was really loose. And that means the wave is going to move really slow. If I increase the tension, watch what happens now.
Like that was more.
It was faster, wasn't it?
Yeah.
And then if I do like this, it'll do what? What's it going to do now?
It's gonna go even faster.
Really fast. And
I can't even see it.
And just like this, the same way, it doesn't matter how big the wave is, the wave gets there in the same amount of time because there's only one thing that determines the speed of the wave, and that's the medium. If you change something about the medium or change what the medium is, then the wave speed can change. And that's true with all waves, sound waves, water waves, anything like that. It's the medium itself, what the wave is moving through, that controls the wave.
So if the medium changes, there's a lot of things that can change about the medium, about the thing that the wave is moving through. But that is the only thing that can change the speed of the wave. Nothing else changes the speed of the wave. The frequency changing doesn't change the speed of the wave. The wavelength, the amplitude, the volume, nothing else changes the speed of the wave except for the medium itself. So we're almost done here, but now you understand, at least in a rope, that the only thing you can do to change the speed of that wave is to change the medium. But you might be like, well, what does that mean practically? Well, let me show you several examples of what that means. So once again, that means that the only way for a wave to change speed is if the medium changes. And there's basically two different ways to change the medium. One is to make the wave move through a different medium altogether, right? So the first example I have for you with that is light bending in water. So check this out. If you look at this guy in this picture, clearly there's something off here. It looks like his head is cut off, but it's not obviously happening. He's in a pool with a glass side, and we're going to talk about this more later on, but effectively what's happening here is that light is traveling through water, and then it's coming through this glass, and then it's coming into air. There's three different mediums here. The medium changes the speed of the wave, and for reasons we're going to talk about later, when the speed of light changes, it also changes directions. It bends so that your mind thinks this guy is over here, his body is over here, but it's actually not. Clearly his body is right here. It's underneath his head. The light from his head is not going through a different medium. It's coming straight to the camera lens through air only. So this is an example of light going through different mediums and bending because it's changing speed. Here's another example. Put a straw in a glass of water. Looks like the straw just got cut in half. Well, it didn't. Again, the light from the straw is coming through the water and then through the glass and then through the air to your eyes. When the wave changes mediums, in this case goes through a completely different medium, it changes speed. And light specifically, when it changes speed, it also changes direction. That's called refraction. And we're going to talk about that later. But this is an example of light changing speed because it's going through a different medium. Sound in different materials. You might not have even ever thought about the fact that sound can move through different materials. Right now, the medium for my sound is air, but check out this pretty cool demonstration here. This is a depiction of a sound wave traveling in different media, and I'm going to start it over again because you almost didn't see it. The wave starts at the very beginning of the video, and you'll see it travel through these mediums as a compression wave. Watch steel first. Really fast. And then water. Look what's happening with air. So you need to first of all understand this is a depiction of a compression wave. I've told you that sound is a compression wave. And what happens is basically one molecule hits the next one, that one hits the next one. And that's the way that these waves are propagated. But what I want you to see here is that sound is super, super fast in steel. Almost 6,000 meters per second. Water is 1,500 meters per second. Now look at air. A lot of people don't realize this, but sound, you almost can't get slower than sound in air in terms of sound, the speed of sound in any material. 343 meters per second. Now that's fast compared to what you or I can run. But compared to what sound moves through on a daily basis in other materials, sound in air is notoriously slow. Here's another example of that. I want you to notice as you watch this video of lightning, notice that you'll see the lightning first and then you'll hear it second. And you've probably seen that before. So again, the reason this is happening is because sound travels so slowly through air. When you see the lightning first, what you're seeing is the light waves traveling through your eyes. And we'll talk about light later, but light reaches you almost instantaneously. It's not quite. It does take some time to get there. But light travels super, super fast. And it takes much, much longer for the sound to reach you because sound in air is very slow. You might have noticed the same thing if you're sitting in the center field at a baseball game. You see the hit first, and then you might hear it about a half a second later. So that's an example of different sound in different materials. Let me see if I had something else over here. Yeah, so if you look at this chart, speed of sound in air is just about as slow as you can get, 330, 340 meters per second. Notice the temperature here. We'll talk about that in a second. But water, gold, brick, wood, all the sound can go through all of these things. Incidentally, steel really, really fast. You can hear a train through the steel train track way before you can hear it in the air because sound is traveling so much faster through the track. Now, it's not going to be as loud because the molecules of steel can't move as far as air can, but the sound travels very fast. Another example of speed changing. So we talked about changing to a different medium. You can also just change a characteristic of the same medium, right? So we keep the same medium, but we can change something about that medium. And the first example I've already showed you is changing the tension in the rope. It didn't change what the medium was, but I changed something about that medium. So let's look at air temperature and sound. Let's see. Oh, it was this one here. Sorry guys, I have this graph. Just a simple graph here that shows you when the temperature increases, the speed of sound actually increases as well. So it's not a huge increase, but for some applications it's important that on a warm day, somewhere 30, 40, 45 degrees Celsius, sound travels at about 350 to 360 meters per second, whereas if it's a freezing cold day, we're looking at 330 or even lower depending on the temperature of the air. What else do we got? You might have seen this before. Look at this picture. Look at how all the trees in the background look. Now I know we're focused on the fire, but you can tell it's kind of blurry. Let me play this video for you. Look at the plants behind here. If you watch them closely, you can see it looks like they're dancing. It looks like they're moving around. They're wavy. You may have wondered what this is for. Well, what's happening is as the heat from this fire rises, it changes the temperature of the air above it, which means it changes the density of the air and it changes the pressure of the air. So the light that's traveling to this camera lens from this plant is having to go through this higher temperature air right here. And as it does that, that's a change in the medium, which means that the wave changes speed. And as we saw in these earlier examples, when the wave changes speed, it changes direction, right? Now, this is a big change in direction because this guy looks like he's moved way over. What's happening here is there's just little small changes in direction, and they're variable because the air molecules are moving. But the direction is changing just enough to where to your eyes and your brain, it looks like all those plants are moving and they're dancing around. So almost done here, and you might think like, wow, there's a lot of ways for waves to change speed. Yeah, there are, and there are some ways for waves to change speed, but for you and me in a normal situation, what this really means is that since these medium changes don't happen very often, most of the time we consider a wave speed to be constant. In other words, that means the waves for you and me, like if we're at a concert, if we're listening to each other talk, waves in normal situations that are traveling through the same medium and everything about that medium is the same, that wave travels at the same speed. And this is a great example of that. At a concert, all sounds are traveling to your ears at the same speed. It doesn't matter if they have a higher frequency, a lower frequency. Think about the bass versus the high notes of the electric guitar. If they're loud sounds, if they're soft sounds, if they're mellow sounds, there could be lots of things to change about the sound. But since they're all traveling through the same medium, which is air, at the same temperature, at the same density, all the air in that concert hall is basically the same, then that means they all reach your ear at the same time because they're traveling at the same speed. And that's really important for your ear to make sense of the speed. So this is what you need to know about waves.